the issues of the memory array design. So this is more related to the peripheral circuits design, because for the memory system to work, you have the memory technology and also the peripheral circuits. So we're going to talk about the peripheral circuits. In particular, we're going to talk about the sense amplifier, which is a key block to read out the memory data. And then we're going to introduce this MV-scene simulator to benchmark the memory array design. And you have one homework, I think last homework, to use this simulator to run some simulations. And towards the very end of the semester, we're going to discuss some of the new applications of those memory technologies beyond the memory, let's say. So those are the trends in the industry as well. So the first topic is to use those non-volatile memory to do the, let's say, cache or logic operations. And also some of the reconfigurable logic can be built with those non-volatile memories. And the very end, we are going to have two lectures on the hardware accelerator for the machine learning or deep learning using those memories. So that actually relates to my research. So my research is mostly to the very last topic, the hardware accelerators for the machine learning or deep learning. So that's a hot topic in the industry these days. Okay, so that's pretty much the topics we're going to cover in this semester. And this is a tentative schedule. And I will not go into the deep details of this table. But we have some lectures maybe covered by the guest speaker because I have to travel for some conferences or to meet the sponsors of the research. And also we are going to have the fall break and midterm exam and also Thanksgiving. So we have some classes missing here in this table. We'll roughly follow this schedule, but of course we can adjust the schedule as appropriate when we progress.
I think where the midterm is the fall break. I think fall break is 15.
Fall break, as I check, is October 8th and 9th. Yeah, maybe I'm wrong, but I remember it's next that time. Any ideas? No idea. So fall break only 2 days. It's not like one break, so 1 week.
Yeah, it's 15 to 16.
We can double check that. Yeah. We can adjust that later. Yeah, it doesn't matter too much. Yeah means what?
14 to 15. Fall break.
14 to 15?
14 to 15 is fall break.
Okay, then we can adjust that later. Okay. Because last year, I think it was this. So, yeah, maybe it changed. All right, so any other questions? This is more logistics. Okay.
Professor, I have a doubt. So in this course, will we be going more in terms of device physics or in the circuit level? So like device physics like energy state diagrams or?
That's a good question. So it's, I think it's mixed, so both, I would say. So if you look at the topics here, the SRAM and DRAM are more circuit level because they are more mature technology, and you know it's just transistor, right? And capacitor, for example. There are not too much physics there, a little bit. As we go to the flash and the emerging non-volatile memories, those will be more device physics there. So it's mixed. Does this answer your question?
Yeah.
And this reminds me, maybe I should do another survey. So how many of you are with the, let's say, major primary area in the nano or this macro area? How many of you are with the, let's say, VLSI? So let's say nano first. How many of you are with nano? Yeah. Then the rest are VLSI. about VLSI? Okay, so then I still see some of you don't raise your hand. So which area are you in? Computer architecture? Computer system? Yeah, so 1 or 2. So any other areas I'm missing? No other areas, right? I guess. Okay, I think that's good. So we have mixed devices and circuits. But the first few lectures are more circuit driven, I would say. Okay, so that's for the logistics. Now let's get started on the real technical discussions. Actually, first lecture is not that technical. It's more like an introduction overview. So this is overview of the memory technology. And this is the outline. Firstly, we are going to see one example. Let's say the memory components in a smartphone. And then we will talk about an important concept, which is memory hierarchy. So we're going to use this memory hierarchy as our, let's say, storyline of this semester, because we are going to discuss different technologies to serve this memory hierarchy. And at the very end, we are going to talk about the concept of the array efficiency and some chip examples to see the real memory chips. Okay. So first of all, for the VLSI system, so actually that's 3 building blocks of a VLSI, or let's say computer system. So we have the computation units, like for example, your ALU, or let's say the logic. And then we have the memory to store the data. And then we have the communication between the memory and logic. So like the interconnect routing and I/O. So basically, if you look at the computer system, or let's say a VLSI system, so those are the 3 building blocks. And historically, I think most of the ECE curriculum focus on the computation. Like you have the digital design or the microprocessor kind of courses. Not too much discussions on the memory. But I think, as you see in our examples later, so nowadays the system's performance actually is limited by memory more than on the logic or the computation. So that's why I think it's important to have this kind of class to talk about the memory technology and the applications of the memory into the new applications. So let's look at one example. This is a tear-down analysis of a smartphone, Samsung S4, which is an old phone, but you know, the components are still there in today's smartphone. So we're going to use this as one example to talk about the components in this system, and we are going to look at what kind of memory we use. So this is you know, after you open the phone, and here are some of the internal look of the phone. You have the circuit board there, and if you look at this circuit board, those are the chips, right? Packaged chips on the circuit board, and there are many units there. Of course, you can imagine you have the processor, right, and then some memory. And here I just want to highlight some of the blocks here. For example, this red one, can you guess what's that? The red one here? Can you guess? It's written there, but it may be too small for you guys to sit in the back. So can you guess what is the red block? So maybe you can see this one, okay. It says 2 gigabytes LPDDR3 DRAM. But actually in this particular design, this is a package with the processor and the DRAM together. So here, this is a processor by Samsung. You know, Samsung names the processor. It's very hard for me to pronounce this. How do they call this? It's not, right? So anyway, so this is the processor co-packaged with the DRAM chip in this particular design. And that means within this package, there are two chips. One is the processor, one is the DRAM.
Are these generally two separate silicon die then? They're not
Yeah,
both the
yeah,
same die?
of course, two dies. Yeah, this is integration at the package level. So this is the DRAM, and then this green block here is 64 megabyte mobile DDR DRAM plus 16 gigabyte MLC NAND flash. So this is another co-package here. So there is a small DRAM packaged with the flash, 16 gigabyte NAND flash in this green module. So this is the major block in this circuit board. And here we see some terminologies here, like for the DRAM we have this, of course you know 2 gigabyte is the capacity, and LP is for low power, and DDR3 is for the double date rate. So we're going to discuss those terminologies later when we talk about the DRAM. What is the DDR? What the DDR3 means? And today you have DDR4. What's the difference between DDR3, DDR4, and there's many kinds of DDRs actually. So we're going to learn those in more details. So today I'm not going to discuss the details of that, but this is what we are going to learn as a part of this semester. And then for this green ones, this 64 megabyte DDR DRAM and then 16 gigabyte MLC. So it seems like in this particular design, this small capacity DRAM is used as a cache for the NAND flash in this case. And again, the terminology is like the MLC. We are going to discuss that in more details later when we talk about the NAND. The MLC stands for multi-level cell. So we are going to discuss that in more details later. Okay, so of course on this circuit board we have other modules. So like this Broadcom, you know, for the Broadcom chip for the Wi-Fi. So it's a separate chip. There are many other things on the circuit board. And this is the front side of the circuit board. And then this slide is the back side of the circuit board. And on the back side you have other chips as well, mostly for like the power management and some communication like NFC and the LTE, those kind of communication chips, transceivers on the back side of the circuit board. Different chips from different companies you can see here, like Broadcom or Maxim or Skyworks. So different chip designers. Okay, so any questions? So then the next question here, what is the breakdown, let's say, in terms of cost for this smartphone? So at that time, probably this is 2013, and the total cost is like $200 for this smartphone. Of course, they sell you like 500, 600, but the actual cost is maybe 200. And here is a breakdown of different components of the smartphone in terms of the cost, dollars. And can you guess what is the most expensive component? Don't look at the, I mean, so can you guess what is most expensive component at that time? DRAM flash? Actually, no. So here you see here this guy, display and touch screen. At that time was $70 out of this 200. I don't know if it's still true for today's smartphone. Maybe this price lowered down a little bit, but still, the smartphone, you have this big screen. This probably if you use the OLED, the organic LED, then that is kind of expensive. And the next one actually is the memory components. Here, the memory components typically the NAND flash plus the DRAM. So those are the separate chips, but combined at that time like $28. It's kind of equivalent with the processor here. So the processor is like $30. The Samsung one, or the Qualcomm Snapdragon at that time $620. So the memory components actually comparable or even more expensive than your processor. So this is the major cost for the smartphone. Of course, you have other modules like the wireless sections, and also the battery, power management, and so on. So still, I think today the memory is important in this kind of mobile system, like your phone or your tablet, because when you change the option of your SSD, right, from 64 to 128, or from 128 to 256, typically they will charge 100 more, right, for you. Of course, the cost is not 100 more, but typically when you buy phone, right, different options for the storage, then they're going to charge significantly higher because of the different capacity of the flash of the DRAM. Okay, so any other questions here? So just a concrete example to introduce the memory components in the system. And then next, we are going to discuss the memory hierarchy. So memory hierarchy means that in the system we have different levels of the memory. And here we have, let's say, on the chip with the processor. This is the chip, processor's chip. This can be your CPU, for example. On the CPU chip, you have some embedded memory there, and they are close to your processor. So typically, they are the caches, and the technology to implement the cache is mostly SRAM. And sometimes we have the embedded DRAM for that as well. But even with the cache, we have different levels. We have L1, L2, and L3 cache. So level 1, level 2, level 3. And here, for example, you see that we have the first level of the memory is the register here. And then we will have level 1, level 2, level 3. So all of those are on the chip with the processor. Here the processor, let's say the core. Let's say the ALU for the multipliers, adders, your logic basically. And then off the chip, we have the main memory. This is like the DRAM. So we have this DIN. We are going to discuss this later. It's called DIN. You see this kind of a DIN, and you can insert that into the motherboard, the slot on your motherboard. So this is the DRAM. And this is for the main memory. And after that is storage. And we have the flash-based SSD, solid state drive, and then the disk So still sometimes you have the hard disk drive. So this is more for the storage purpose. And this is the spectrum of the memory technologies into this memory hierarchy. We have different levels. And why do we have different technologies, let's say, for this memory hierarchy? Any ideas? Why do we have different technologies?
Balance speed and cost.
Yeah, exactly. So of course, ideally, you want memory to be fast and also low cost. Low cost, in other words, you have large capacity. So those two are, let's say, those two metrics conflict with each other, as you see here. So here, this is the speed, let's say the read or write speed, and then versus the capacity, size of the memory. And the register is the fastest. So this is the same clock speed as your CPU, the same cycle. Here the CPU cycle is the same as your clock for the CPU. But the size may be only hundreds of bytes. As you go to the L1 cache, then you go to like 1 nanoseconds or few clock cycle, and then you can get like kilobytes or maybe hundreds of kilobytes L1 cache. And then you go to L2, you are going to maybe have a few nanoseconds, and then you can go to like 1 megabyte. And then you go to L3 cache, then you will have like maybe 10 nanoseconds, and then the capacity can go up to maybe 8 megabytes or 60 megabytes, still meg, okay, at the range of mega. So those are the typical sizes for the caches. And one question here. So for the caches, we have L1, L2, L3, but actually all of them are implemented with SRAM technology. But why do we have different levels of the cache, and what makes the difference between those levels? Any ideas?
Location of the cache.
You?
Location of the cache.
Can you say it again?
Location of the cache being inside the processor package or outside the processor package.
Yeah, not really, but
The L1 cache has the instructions which are more frequently used.
yes.
So that's why it's closer to the processor.
Yes.
So they're accessed closely, and the others will be accessed only when required.
Yes,
And then they'll be
yes,
shifted
yes.
accordingly.
Of course, you save the more frequent data close to your processor, like L1 cache or even register, but their size is limited, so then you have to save some data in the lower level cache or even in the DRAM. But my question is, what differences do you have in those SRAM cells? Because those are the same. If you look at the circuit schematic, there are 6 transistor SRAM cell. What makes the difference in the L1, L2, L3? Of course, we are going to discuss that in the lectures on the SRAM, but here just one early question for you.
Capacity, so the larger the capacity, the slower the level of cache is.
Yeah, so you say you have different sizes of the SRAM, let's say L1, L2, L3 caches. You have different capacity, you have different speed. So what makes the capacity different? What makes the speed different in terms of the transistor? What characteristics of the transistor different?
The width.
Yeah, exactly. So you tune the W over L of your transistor, and then you can tune the speed and the area density, right? So you see the trade-off. If you want fast, then you are going to size up the transistor. Then, of course, your area is large. On the same chip area, then your capacity is smaller. So that's why you use that for L1, right? Then you can have the trade-off by sizing the transistor. So then we go to DRAM, right? Off-chip DRAM. And sometimes we have embedded DRAM. We are going to discuss that later when we talk about the DRAM. But mostly the DRAM is off-chip. Off-chip means off the processor's chip. It's a different chip. Okay. And the DRAM, typically you have like 10 to 100 nanoseconds in the access latency speed. Typically like 40 nanoseconds, 50 nanoseconds. And the size of the DRAM, you know, these days you can have like 8 gigabyte DRAM or even 16 gigabyte DRAM, right? So it's on the giga level. And then you go to flash. So flash is you can have, you know, these days 128 giga or 256 giga or even 512 giga, and the speed is typically like hundreds of microseconds, tens to hundreds microseconds. So it's much slower, but you get much larger capacity. We're going to discuss what limits the speed of the flash when we talk about the flash later. And then you go to the hard disk drive, which is the slowest, like milliseconds, because in that case, the readout is through the mechanical rotating of your, let's say, hard drive, right? So you have the reader to rotate to seek the track, and then you read the data from the hard disk, which relies on the magnetic domain of that disk. We are not going to discuss the hard drive in this course because that is not really the semiconductor. This is more like the magnetics and the mechanical readout mechanisms. So we are not going to discuss the hard disk in this course. But hard disk is good for, let's say, the very large capacity storage. And here I didn't list one more technology. Actually, in this memory hierarchy, if you go down to the very far end towards the right, so there is one more technology that you may have seen that before. You may, depends on your age, I think. So can you guess what is that?
Tape.
Yeah, exactly. So tape. This magnetic tape. So that actually has the largest capacity. You can store many informations there, but of course it's very slow. And but it's good for archiving purpose. Okay. So the reason is that for the flash, we are going to discuss that later in more details. The data retention is a problem. So you can only store that data maybe for a few years, and after that you may lose your data. Okay, this is not good for archiving purpose, right? So then, still the hard disk or the tape is the most safe way to store the data. So if you want to save your data for tens of years, then you have to go to that magnetic technologies, like the hard disk drive or the tape in that case. Because your flash is not going to work for so long. The reason is that because you will get a new phone every, I don't know, 1 year, 2 years, right? Anyway. So that's why the industry didn't design that for like 10 years or 20 years. So the specs is only for like a few years.